Miao Qianling from Chinese Academy of Science. I'm here to present the research on detecting server-induced client vulnerability in Windows Remote IPC on behalf of the author who cannot attend these conferences. It doesn't work. Oh, okay, sorry. Well, inter-process communication, or IPC, is not a new word. It has been studied in the past year. Traditional security research focuses on exploiting vulnerability in servers, assuming servers are the main target. However, in remote IPC scenarios, the client can have higher privilege than the server, and the server provide data can compromise the client trust boundary, leading to severe vulnerabilities. That's why many server vulnerability discovered, the client-side vulnerability remain largely undetected. Let's go to Windows IPC first. It contains a set of mechanisms which supports the following features: local and remote machine communication, privilege separation, offer flexibility for developers, and policy-based communication. Here is a typical remote IPC in Windows domain scenario. An IPC client named Performance Monitor sends IPC requests from a privileged domain controller. The server, which is non-privileged, sends a response back through TCP. If the server is compromised, attackers can craft a malicious response, pose a security risk to the client. Normally, the IPC client is driven by user clip or input from mouse or keyboard, which client then prepare context for the remote IPC. Therefore, a typical remote IPC workflow goes like this. The user click to generate IPC context. The client sends the IPC request to the remote, and then the client receives the server's response and process the return values. So based on this interaction logic, we can get a threat model in Windows IPC client. It consists of the following key points. In scenario, many IPC client has higher privilege than the server, and the IPC server is untrusted and low privilege. The client is the testing target here. If the IPC client is vulnerable, it will threaten the security of the machine it runs on. An example of such client including Performance Monitor, Event Logger, and Viewer, and others. Let's see a case study of CVE we discovered in the Windows Performance Monitor. When the domain controller uses a Performance Monitor to monitor a low-privilege machine, the machine can trigger a crash on the domain controller. The right shows the relevant code. The red marks indicate where the IPC requests are sent and receive data. The crash happens when the client doesn't properly validate the return value from the malicious server. So IPC is very common, but compared to traditional server-side vulnerability, detecting client-side vulnerability presents different challenges. Here are three key aspects. First, it's difficulty to identify IPC clients from large-scale binaries, especially in closed-source systems like Windows. Unlike server-side testing, where documentation helps identify remote APIs, client-side applications often lack such documentation, making it harder to locate IPC calls. And second, it's essential to trigger as many IPC calls as possible to test various return values, but clients often involve diverse environments, and it's challenging to prepare the correct context for testing. And third, context resuming can be resource-intensive and slow, which makes the testing efficiency another problem. So to address this, our role introduced GLEIPNIR, which can detect Windows Remote IPC client vulnerability efficiently. The process includes three phases: identify IPC client and servers, prepare context, and perform snapshot-based fuzzing. In phase 1, the goal is to identify where the IPC client and the server are located. This also involves establish mapping between client and servers and identify the server ID and method ID on the client side. To achieve this, we first analyze key IPC APIs related on Windows. As shown in the table 1, our task is to locate the call sign of this API in Windows binaries. We use a heuristic-based method to analyze the IPC client APIs, including their call signs, parameters, callers. This allows us to identify which module and function are calling the IPC methods. And next, we analyze the process of these IPC methods to figure out where IPC call will go to which server API. In this way, we establish mapping between the server and the client methods. And in phase 2, GLEIPNIR prepared context for the 3 different types of clients, including GUI and CLI application and public APIs. All of these client types can involve remote IPC call on untrusted server. To trigger IPC call, we first need to generate valid user clip and inputs. To do this, we introduce large language model as a system. By interacting with LLM and pass valid feedback for CLI clients to input, we can make LLM generate effective input to the client, making it generate as much IPC call as possible. For GUI programmers, we employ a UI automator to randomly emulate user clips. In this way, we generate IPC requests and load the prepared context. Here is a working example of using LLM as a system for testing CLI-based client. We provide the initial question and store each interact command to for accurate context for LLM to analyze and generate correct response. And in phase 3, now based on the context we already have, we need to resume the context for each run. As this process is resource intensive, we adopt our memory snapshot-based fuzzing technique. We improve the fuzzer to handle network packets to minimize speed loss. We also develop a customer fuzzing strategy about seed scheduling and determine when to start or stop the fuzz. Here are the main improvements for our fuzzer. For mutation and injection, the fuzzer controller gets mutate return value for the mutator and ingests them into the memory using a hook programmer. For execution and monitoring, it resumes the client process and uses free monitor to collect data and decide when to continue or stop the test. For interaction and scene management, the controller either starts the next mutation or set or stat the CQ value for further testing. For exception and dirty page monitoring, monitor checks exception and memory changes for manual vulnerability analysis and control when to store the fuzzer. And in the evaluation, we answer the following question: how effective is GLEIPNIR at identifying client, preparing context, and detecting vulnerability? How efficient is GLEIPNIR in fuzzing client? How it compares with other fuzzing approaches? We also perform application study for GLEIPNIR. For question 1, GLEIPNIR identified 145 public API and 129 servers out of a total 2834 IPC calls. RPC and CON are the primary IPC methods. And for question 2, GLEIPNIR prepared context for 2834 IPC calls and more than 500 unique remote methods. A total of 2169 IPC requests are triggered. And for question 3, 14 vulnerabilities have CVE numbers and 19 have been confirmed by Microsoft. This vulnerability causes memory corruption, which can lead to remote code execution and information leakage. And for question 4, figure shows the testing efficiency of GLEIPNIR across 18 applications. After 24 hours, all applications coverage stabilizes. And for question 5, we design comparison experiment with common Windows fuzzers like WinAFL and Winning on remote IPC client for programmer, mainly focus on the fuzzing performance and coverage. You can refer to the paper for more details. And for the question 6, during GUI testing, we compare our original dev first and IPC-based improved strategy with random strategy. The result shows that our strategies are far more effective in triggering IPC calls and detecting vulnerabilities. And in summary, we introduced GLEIPNIR, which focuses on finding client-side vulnerability, an area that often overlooked in research that usually focus on server-side vulnerability. The solution using static analysis to find IPC clients and servers and mapping them together. It also leveraged LLM and UI automation to prepare testing contests. In testing 66 client applications over 7 days, GLEIPNIR identified 25 vulnerabilities. The identified vulnerability led to 14 CVEs and a total bounty award of $36,000. Thanks for listening, and if you have any question, you can contact the email here.
All right, thanks to the speaker.